I'm going to be talking about how to use latent class analysis to help with market segmentation. I'm planning to start by looking at how latent class analysis works and contrasting it with cluster analysis, after which I'm going to present an application looking at what research suppliers think their clients want. The basic idea with latent class analysis is to, I'm sorry about that skipping forward, is to take a whole lot of data, such as responses to multiple questions, and convert that into a segmentation, where a typology of consumers is identified. In this sense, latent class analysis is identical to cluster analysis. They both identify a whole lot of data and turn it into segments. However, as you will see by the end of this session, latent class analysis dwarfs cluster analysis. This is because latent class analysis is theoretically superior. It has clearly stated assumptions, whereas cluster analysis contradicts some elementary laws of probability, in particular something called Bayes' theorem. And more pragmatically, latent class analysis software is superior in that it's been designed so it can deal with lots of different types of data, be it categorical, conjoint, max, diff, and so on. You can simultaneously form segments with both categorical and numeric or any other types of data, which is referred to as mixed data. It can automatically deal with missing values, and if you're clever, you can get it to remove response biases from the data. To better explain how latent class analysis works, I'm going to start by reviewing how k-means cluster analysis works, which, as I'm sure many of you know, is the main cluster analysis tool that people use for segmentation. In k-means, we start by specifying the number of clusters, and that's indeed what the k in k-means stands for. I have some data shown here, and if you look at the data, you can probably see two general clusters of dots, and so in this example, I will specify k as 2. We then need to randomly allocate respondents to the clusters. And I'm showing this with little black and white dots. So everybody with a black dot is in the black cluster and everybody with a white dot is in the white cluster. The next step is to compute the cluster means, which I'll place on the map now. The cluster means are just the averages of the dots in the particular cluster. So you can see that there are more black dots on the left-hand side of the plot. Therefore, the cluster mean for the black dots, shown by this cross here, is closer to the left, whereas there are more white dots on the right-hand side, and so the cluster mean is shown closer to the right. Then we move respondents to their most similar cluster. So you can see here these two white dots are both a lot closer to the black segment mean than to the white segment mean, and so they should be moved into this segment. And similarly, over here, these 4 black dots are really a lot closer to the white cluster, and so they should have their color changed, or to be more precise, they should be reallocated to the white segment. And having reallocated the response to the segment, the next step is to go back and recompute the cluster means, because you can now see that this black cross isn't in the middle of all of the black data points, and so we need to move this mean into the middle, and similarly we need to move the mean from the white dots into their middle as well. And then we go to the next step and try and reallocate people to the most similar cluster. In this case here, there's nobody to move. They're already all allocated to the most similar cluster. And we can keep going through this process of computing the cluster means, reallocating people, until the means don't change, which has occurred here. On the left-hand side of the screen, you can see the solution or the method that we've used for k-means cluster analysis. On the right-hand side, I'm contrasting it with how latent class analysis works. It's the same basic process. We begin by specifying the number of classes, which is just another name for clusters, or segments if you like. We randomly allocate people into classes. We then compute the class parameters, and this is just another name for computing the cluster means. And then we come to the first different step, which is whereas in cluster analysis we allocated people to the most similar cluster, in latent class analysis we instead compute the probability that each respondent is in each class. So we might, for example, identify that a respondent has a 95% chance of being in one cluster and a 5% chance of being in another cluster. Then, as with k-means, we go back to the previous step and update the class parameters or the class means. And we do this taking into account the probabilities we've computed. So the respondent who has a 95% chance of being in one class is given a weight of 0.95 when computing the mean for that class, and given a weight of 0.05 when computing the mean for the other class. And finally, we allocate respondents to the classes with the highest probabilities, and this ensures that each person is allocated to one and only one cluster. At the top of the page, I have the cluster analysis that we computed together only a few moments ago, and underneath I have a latent class solution for the same data, and as you can hopefully see, it's exactly the same solution. And this is a very, very important point about understanding latent class analysis. If your data contains clearly identifiable clusters and your data is appropriate for use with cluster analysis, you'll actually get the same result whether you use cluster analysis or latent class analysis. In situations where cluster analysis is appropriate, latent class analysis will give you the same result, as long as you press the right buttons. However, latent class analysis dwarfs cluster analysis, and this is because latent class analysis can be used in lots of situations where cluster analysis cannot be used. One of the key ones relates to missing values. I've got here 8 respondents. Each respondent is shown by a row, and I have 4 variables shown by a column. Question for you is, how many clusters or classes can you see in this data? When I look at it, I see the first 2 respondents have got the same basic data, so they form a class together. The next 2 respondents have also got the same data, and they belong in a class together. But the last 4 are a little bit more problematic because they have missing values as shown by the dots. However, if I look carefully, I can see that these last 4 respondents have all got a rating of 1 for the first variable, a rating of 2 for variable B, a rating of 2 for variable C, and a rating of 1 for variable D. So, once I take out the missing data, I see that they're actually identical, the last 4 respondents. And if I get a latent class program to analyze these respondents, it will identify that they all belong in the same segment. As can be seen here, the first 2 respondents are shown in classes 1 and 2. The second 2 respondents are shown, the first 2 respondents are shown in class 1, the second 2 in class 2, and the last 4 have been grouped together in class 3. And we can see the averages shown to the right, where these averages just reflect the average response of people in the class. But what happens with cluster analysis? I'm now showing you the dialog options that I specified or selected, I should say, in SPSS. And I've used SPSS for this because it's probably the best of the widely used k-means programs. I've specified that there are 3 classes, and more importantly, I've specified an option that I want it to automatically deal with the missing values. You can see to the right here, we've got the original data shown again, and the classes as identified by SPSS shown as well. You can see that it has given a class for every respondent, so it has dealt with the missing values. However, note that the first 2 respondents are in class 1. The third and the fourth are being combined into a class together called class 3 in this case, and that makes sense. They should be grouped together. But respondent 5 has been allocated to class 1, 6 to 3, 7 to 1, and 8 to 3. So the 4 respondents who, by eye, you can clearly see belong in their own segment, have been pushed into the other segments, even though we told SPSS we wanted it to group 3 clusters. If we look at the table of cluster means, we find that the cluster means show us cluster 2 has got no data at all. It's entirely missing data. So although we told SPSS to find 3 clusters, it only managed to find 2. The reason for this is the way that SPSS deals with missing values, and the way that the vast majority of researchers who use k-means techniques deal with missing values, is it first forms the segments only using respondents for whom there is complete data, and then in a second step it allocates respondents with missing values to the most similar segment. And a lot of researchers use this same process in a slightly more complicated way, where they'll first use k-means cluster analysis on respondents with complete data, and then use discriminant analysis to allocate the remaining respondents. And as we can see in this situation, we get the wrong answer. A more technical area, but just as powerful of latent class analysis, is the ability to play with what are called distributional assumptions. This is a fancy way of saying that within latent class analysis, we can tell the program how we wish it to interpret particular types of data. So thinking about a rating scale, and here I'm going to show you for 4 respondents who have rated 3 statements, and they've been given a choice of giving them a response of agree, neither, or disagree. Now, when you adopt a categorical assumption, a latent class model, what happens is the maths of the model at an underlying level. Just work out which respondents are similar by looking at how many matches they've got. So if you look at the data here, we can see that these first 2 respondents, shown in rows 1 and 2, agree on A, they agree on C, but they differ on attribute B, and consequently they agree on 2 points. Respondents 1 and 3 also agree on 2 points, which are A and C, and they differ on B. And so you would say that 1 and 2 are just as similar to each other as 1 and 3. An alternative assumption is to treat the data as numeric, assigning values to each of the categories and computing differences. For example, we may assign a 3 to agree, a 2 to neither, and a 1 to disagree. If we do this, we find that respondents 1 and 2 have a difference of 1 between them because they differ by 1 scale point on attribute. Sorry, they have a difference of 2 between them, because they differ by 2 scale points on attribute B and nothing on A or C. Whereas respondent number 3 differs on only 1 scale point from respondent number 1, which is they differ on attribute B, and consequently they're more similar to respondent 1. And another assumption we can make, which we'll use to good effect later, is to just look at the data as having relativities. That is, we treat the ratings as if they're rankings. And the surprising thing here is that even though respondents 1 and 4 didn't give the same response to anything, if we assume their data as rankings, we actually assume they're identical, which is they both gave A and B the same rating. That is, respondent 1 gave it a rating of agree for A and agree for B, whereas respondent 4 gave a rating of neither and neither. And their ratings they gave for A and B were both higher than the rating they gave for C, which was neither for respondent 1 and disagree for respondent 4. And so you can see that we can make different assumptions about what the data means, and they're non-trivially different. They give different interpretations of the data, which we'll return to in a sec. Now that may have been a little bit technical, but I'm about to get into a slightly more technical situation. And for those of you that don't like probability and things, just tune out for a couple of moments, check your email. I'll tell you when it's time to wake up again. As I mentioned before, latent class analysis differs really in how we compute the probabilities, and I'm going to show how that's done using some categorical data. We have 5 variables where people have had the option of agreeing or disagreeing to each. If we look at the first 2 respondents, the first one has got scores of agree, 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 disagree, and the next has agree, agree, disagree, agree, and so on. And we're going to look at how to compute the probabilities of a person being in a particular class. So looking here at respondent 6, shown on the left, this respondent disagreed with the first statement, agreed thrice, and then disagreed. If we look at the parameters, we can see that the first segment or class contains 2/3 of the sample, the second 1/3. And if we look at the individual responses, we can see that in the first class, 40% of people agreed with the first statement, 60% disagreed. In the second class, 65% agreed with the first statement and 35% disagreed. Now, which segment or class do you think our respondent belongs in? I've shaded the actual responses of the respondent in pink. And if you look at the data, what you can see is the respondent's first choice of disagreeing is more consistent with being in class 1 on the shop attribute because people in class 1 were more likely to disagree. But if we look at all of the other attributes, the numbers in the pink in class 2 are higher than they are in class 1, which is to say that the respondent's data is more consistent with being in class 2. And so overall, you'd say this respondent is more likely to be in class 2. Being a little more formal about it, the way that latent class analysis actually performs the computation is it starts by making an initial best guess of what segment somebody is in just by looking at the class size probabilities. So we could say that our respondent would be, if we didn't know what data they'd selected in the questionnaire, have a 67% chance of being in class 1 and a 33% chance of being in class 2, and this is determined just by the class size probabilities. The next step is we work out the probability that our respondent would have answered the way he did if he was in each of the classes. So if our respondent was in class 1, there was a 60% chance he would have disagreed, a 40% chance he would have agreed, a 48% chance he would have agreed with the third attribute, 16% and 14%, and 47% for the last attribute called value. If you can remember your elementary probability, we can multiply each of these together, and it tells us that if our respondent truly was in class 1, there's a 1% chance that we would have seen the responses that he's given. By contrast, if he was in class 2, there's a 20% chance that he would have given the responses that he gave. And thus, we can say that looking at the responses that he's given, he's 20 times more likely to be in class 2 than in class 1. And the final step in computing the probability that our respondent's in a class is to multiply together these numbers and these numbers. So we can see here that the class 1 probability is the 67%, which is the number on the far left, for class 1 multiplied by 1%. For class 2, it's the 33% multiplied by the 20% figure. And to force the numbers to add up to 100%, I've just summed them up and put them on the bottom side of the fraction, and we then get probabilities that our respondent will be in class 1 of 9% and class 2 of 91%. So that's the basic way that it works out what probability somebody's in a class. So those of you that are checking your email or did fall asleep, now it's time to wake up, and we'll get on to a very interesting application. This application is a preview of some of the results from Greenbook's latest GRIT survey. I've got a sample of more than 1,100 market researchers, and they were asked, how important do you think it is that each of the following, how important do you think each of the following attributes is to clients when they select a research provider? And they were given a 5-point scale. The complication was that due to questionnaire length, people were only shown 15 of the 25 attributes. If you've been paying close attention or you've done a bit of segmentation using cluster analysis, you'll know that we've got a problem, and we can't apply cluster analysis to data where we've got missing values for every single respondent. However, we can apply latent class analysis for the reasons that I've explained a bit earlier. This first output contains 3 segments. The latent class program that I used automatically selected 3 segments using something called the Bayesian information criterion, which is the way that most latent class programs will work out how many clusters or classes there are. In this output, it's been computed using the numeric assumption, which is to say that a difference between, say, a 5 and a 1 is considered to be 4 times as big as a difference between a 5 and a 4. On this chart, I'm showing top 2 box scores. I've shaded anything orange where the segment's got a score that is above the average for the total sample. And the intensity of the orange reflects the level of significance. So a really dark orange means a really small p-value, and a paler orange means it's closer to being marginally significant. Now, at first blush, we seem to maybe have a useful result here. If you look at segment 3, we can see that it's skewing on 2 attributes, having knowledgeable staff and high quality analysis. It's a bit harder to see, but there's a pale orange for segment 2 for price, telling us that this segment is skewing a little bit towards price. However, if you look at the data a bit more carefully, it becomes clear that this segment's actually quite meaningless. Our skew that we've got for segment 3, scores of 96 and 91%, is actually lower than the score of segment 1. If we look at the price skew for segment 2, that's 68%. Well, it might be a big score on price, but it still means that 32% of the people in that segment didn't select price as one of their top 2 boxes. And thus, this segmentation doesn't seem to reflect what people think. It seems to tell us more about how they respond to surveys. And market researchers, just like respondents, seem to be prone to selecting particular scale points. And what we've identified really here is that segment 1 are people who think everything's important, and that's the key distinction, the way that they respond, or what we might call a response bias or a response style. Now, if we were doing cluster analysis and we didn't have our missing data, we'd get a solution just like this. Because we're using latent class analysis, we can play around with our assumptions. Here, I'm showing what happens when we change to a categorical assumption. We've got 2 segments this time. If you look at the data, we can see the first attribute at the top, lowest price, there's a stronger difference now between segment 1 and segment 2 than we identified in the previous slide. But we still seem to have a response bias. The only thing which discriminates between segment 1 and 2 really is that segment 2 has got a higher score on price, But again, we have this problem that a third of people didn't select price as a top 2 box in segment 2, so we really cannot accurately describe segment 2 as being focused on price. And the real explanation seems to be that, again, we've identified one segment who like to tick the higher boxes than another segment. This is where we can apply the ranking assumption. So we'll try a third assumption now. Unfortunately, we get a better solution this time. The key thing that hopefully jumps out at you here is, whereas the previous 2 solutions had one segment which was primarily orange, here neither of the segments are owning orange. Look at the top row, look at the price. Here we have a much bigger difference between segments 1 and 2 on price than we've seen before. But we have other differences as well relating to price. So segment 1, strongly interested in price, previous experience with clients and suppliers, rapid response to requests, understanding, listening, flexibility, familiarity with the client. Choose the jargon of economics. Segment 1 are people who believe that clients are primarily concerned with transactional costs. Or, in simpler language, segment 1 believe that clients just want an easy life. They want to be able to easily buy research and have minimal effort and hassle. Looking at segment 2, down here we can see that it's skewing in terms of attributes like high quality analysis, data analysis services, using sophisticated techniques, high quality data. And so the researchers in segment 2 are those who believe that clients are more interested in high technical quality of the research. So just to recap this application, we started with data containing a very large amount of missing values. In a traditional cluster analysis type segmentation, we would have had to walk away or perhaps do something a bit dodgy like imputing the data. In latent class analysis, the latent class model automatically dealt with the missing values, and when we got a trivially or uninteresting solution to begin with, we've been able to change the assumptions and create a more useful segmentation. There are quite a lot of different analysis packages that you can use today to do latent class analysis. I think overall the best of these packages is one listed at the bottom called Latent Gold. If you're trying to do segmentation, I probably think Q might be the best, but I could be biased there. Q is the only one of these tools that's primarily designed for segmentation purposes. All of the other tools have got different types of application in mind, such as predictive modeling and market simulation and the like. The one key thing that I should point out is the technique that we found quite useful at the end, where we treated the data as ranking, is only available in Q. So to summarize, latent class analysis is a lot bigger and a lot better than cluster analysis. There are few, if any, real situations where you'd want to use cluster analysis to segment these days. Thank you. And we will throw it open to question time.